In this video, we're going to dive a bit deeper into the idea of kernels, which came up in the last video in the context of dual support vector machines. In the last video, we talked about how the SVM primal problem has a dual form, which is another optimization with very different looking objective function and constraints. And the form of the dual optimization problem has box constraints on the dual variables, and it only considers inner products of the data vectors. So that leads to the idea that we can replace those inner products with kernel functions. And the idea is that a kernel function is going to be some function that relates to data examples or data vectors such that it represents some form of inner product in some other mapped feature space. And I talked about that at the very end of the last video and didn't go into detail, so we'll look closer at it in this video. So this is the form of the dual SVM, and when we add a kernel function and replace these inner products, we get the kernel SVM. So this video is going to be organized as follows. We'll talk about feature maps and nonlinearity. So why do we want to map to a different feature space, and how does that get us richer decision functions? And then we'll talk about how to efficiently compute certain kernel functions that are very popular in the application of support vector machines. In particular, we'll talk about the polynomial kernel, and we'll talk about the Gaussian radial basis function kernel, or the RBF kernel. And then in that discussion, I'll correct a mistake I made in the last video where I described the feature space that the Gaussian RBF kernel maps to, and what I described was incorrect, and I'll show you exactly why it's incorrect and what the correct mapping is. So let's start thinking about some one-dimensional data to keep things simple. So imagine that we had some data that is on the one-dimensional number line, so that's x values, which will just be a single scalar for each example. And we want to use if we use a linear classifier or a linear decision function, then it essentially is going to be some constant scalar times x, where we offset it by some bias, and then we basically just threshold the score by checking whether it's less than the bias or greater than the bias. So if it's on the left of this intersection point, then we're going to predict it's a negative point, and if it's on the right, we'll predict it's a positive point. Okay, and this is fine. This is actually what we do in higher dimensions. This makes a lot more sense, but in one dimension, you can see pretty clearly, what types of data we can exactly separate with this type of linear decision boundary. So if we got data that looks like this, where there's a bunch of blue points on the left and a bunch of red points on the right, then we can do this. We can shuffle or move around the weights and the bias term to fit the decision boundary around those points. So this is great, but now if we have data that looks instead like this, if we have data where there's red points on the left and blue points in the middle and red points on the right, there's no such linear decision boundary that can separate all the red points from the blue points. So no matter how I shift the slope of the purple line, the W, or no matter how much I shift the B, the bias, we're never going to be able to separate all the red points from all the blue points. So at this point, we'll now consider mapping the input x into a different space, a different representation of the same information. And what we'll consider is mapping it to the squared value of the x input. So imagine now that we have x squared. So down there, this is now the x squared line. And the classifier is going to make its decision based on thresholding the w times x squared. And what that would look like is it would basically be some form of parabola-like shape where we're going to have very positive values on the left and very positive values on the right, and some less positive values in the middle. So if we again threshold by the bias, we get that on the left we get we're going to predict positive, and on the right we're going to predict positive, and then in the middle we'll predict negative. So by considering the squared value of the input, we are able to fit something that wouldn't be possible with just a linear separator. Another way to think of this is that we're mapping to a different feature space, which could be higher dimensional or lower dimensional, and then using a linear classifier in that higher dimensional space or in the other dimensional space. Now, it may be higher dimensional because here in this picture we're only looking at x squared, but imagine we also wanted to have a weight on x as well, in which case originally it was one dimensional, now it's two dimensional. So this gives rise to the idea, the generalization of what I just showed you is the polynomial feature map. So you can see here we have, phi of x is going to map to x, which is x1 through xd, and then x times itself, so a bunch of squared terms, so x1 times x1 all the way to x1 times xd, to xd times x1 all the way to xd times xd. So all the possible combinations of two dimensions of the original input. And then there's more terms. I left it off as a dot 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 on the end. There's more. There's third order terms where you have all the possible combinations of three different dimensions of the original input, and fourth order terms, which is all possible combinations of four different dimensions of the input term. So you can imagine, expanding this to as many orders as you want, and as you build more and more, as you include higher and higher order terms, you get more and more nuance that you can fit a classification or a decision surface around. So what is the dimensionality of this now expanded feature representation? So if we think about phi as the full vector, or the output of the phi function is the full expanded vector, it's going to be something like this. It's going to be the sum from with a from 1 to m for an m order polynomial feature map of d to the a. So that's order d to the m, right? There's some lower order terms in that size that become negligible as m grows. So that's really huge. That's really huge, right? A lot of times we want to do, we have a large dimensional input, so maybe we have 1,000 dimensions, we have 1,000 raw features, and we want to use, let's say, the third order polynomial kernel. So that maps to 1 billion dimensions, or on the order of 1 billion dimensions, which is huge. And we definitely don't want to compute something with 1 billion dimensions explicitly. So we'll talk in a minute or so about how to compute that quickly. But before we do that, let's just look at what do these higher order terms buy us. So I showed you a cartoon example in 1 dimension, but now let's look at things in 2 dimensions where things get a little bit more interesting. So here's an example of a quadratic kernel decision surface, where we're weighting all the different combinations of input dimensions and their original input dimensions by essentially what I just set up a MATLAB script to do random weights here. So you can see some interesting shapes here, and a less interesting shape that looks kind of like a Gaussian. And then if we go to third order, we get even more exotic looking surfaces and curvatures that can come out of this type of feature map. So you can imagine how this can be useful. But again, the problem is, as we go to higher order terms, this on the surface appears to become much more expensive than the original linear SVM would be. And again, the way that we get around this, like I mentioned in the last video, is the kernel trick, is the idea that we can compute the inner products, or we're hoping that we can compute the inner products in this high dimensional space in a much faster way. And so here's how we do it. So our goal is to compute something with phi of x, but that's not actually our goal, because remember, we never actually look at phi of x by itself. In the dual SVM, every single time we look at any x, we're going to be looking at it as an inner product. So what we actually care about is this kernel function, which is defined to be the inner product in this high dimensional space. But if we can find a way to circumvent the high dimensional representation, then we can just try to directly compute k of xi, xj. So let's try to look closer at what this inner product looks like. So there's a phi of xi, which looks like this, and then there's a phi of xj, which looks like this. And what we want to do is we want to multiply each entry of phi of xi by its corresponding entry in phi of xj, and then sum them all up. So we want this alignment element-wise. Well, this is just another way of describing the dot product. So here comes the trick. The trick is that we can write out something that looks a lot like this without ever expanding out the full vector. So it looks something like this. So we take the dot product of some vector xi and xj plus 1 and take that all to the mth power. And this is actually the formula for the polynomial kernel, and it's going to get us something very, very close to the original dot product that we wanted, but it's going to be a little bit off because some coefficients might not be the same as what we expect them to be. But those coefficients don't really matter because they can be absorbed by the W weights that will eventually be fitting to these implicitly. Right? In the dual form, we never actually explicitly write out the weight vector in the same way we never think about the x vector or the phi vector, but instead we only think about the dot products. Okay, so let's just imagine, for m equals 2, which is easy for us to think about, what does this look like? And we can write it out just by looking at the FOIL expansion of this quadratic term. So first outside, inside, last, and we get something that looks like this, right? We have the first term multiplied by itself, the middle terms, or the 1 times xi times xj, two of those, and then 1 squared, which is 1. So we get this. And if you look closely at this, you can see that this is exactly the quadratic kernel. Or more precisely, it actually is the dot product of all the quadratic terms, which is on the left, plus the dot product of all the linear terms, which is the middle term, and then a 1, which we didn't have in the original form, but doesn't hurt us in any way and allows for this efficient computation. So you can do the exercise yourself and see how this applies to higher order polynomial kernels, and it works the same way. But again, the 2 in the quadratic kernel adds, creates a coefficient that we didn't originally have, but that coefficient doesn't really matter that much because we're going to be multiplying each of these dimensions by some weight. So another idea you want to keep in mind is that if we want to think about this super efficiently, we might want to work in terms of the data matrices rather than the data vectors. And here we might have a data matrix that's d by n, so each column is an example. Then the polynomial kernel can be just computed, or the gram matrix for the polynomial kernel can be computed just by taking the inner product of that matrix with itself, plus 1, and all element-wise to the m power. So you can see that's a one-liner in MATLAB, but it also reveals how efficiently this can be computed given how fast we have, fast computers are at computing matrix products. So with that, we can look at the next type of feature map we'll be interested in, which is Gaussian radial basis functions. And the way this works is, again, let's look at the 1D line and we'll think about this nonlinearly classifiable data. So one way to form a decision boundary that fits this data is to imagine putting a little bump over each example point. So you put a bump over this red point, over that blue point, over this red point, and so on, and you put a bump over all the data, and then you imagine weighting those bumps. So you use those bumps as the bases for the decision boundary decision function you're going to create, and you just essentially move them up and down. And when you do that, you can form some decision surface that looks something like this. This is just a cartoon, but you can basically shift the function up and down at each point, at each data example. And you again would apply some bias that serves as a threshold, and you can say that everything that is to the left of this intersection point and everything to the right of this intersection point is positive, and everything in the middle is negative. So this is definitely a strange looking way to design a decision surface, but it leads to a kernel function that looks something like this. So it's the kernel between xi and xj, and it's the distance between xi and xj exponentiated and taken, multiplied by -1 over 2 sigma squared. So it's very much, this is the formula for the Gaussian density if xi is the mean and xj is the variable, or vice versa. So this is actually the kernel, and this is a little bit different than what I showed you in the last video. So there was a mistake in the last video where I showed you this, and I wrote this out as if this were the feature map for Gaussian RBF, and it's actually not. So this is a mistake, and there's actually another mistake in it, which is that I didn't negate the exponent in these, but instead this isn't exactly what would get you the kernel function up above. So remember, the kernel function is supposed to mimic an inner product of of some feature map. So what is the feature map that would give us this inner product at the top? And it's actually quite involved, and it would be nice if it was as simple as what I thought it was last video, but it isn't. It's quite more. It's more interesting. I mentioned last video that it is infinite dimensional, which should have been a clue that what I wrote on the screen was not correct, because I showed you a finite dimensional feature map. Okay, so somehow the kernel function at the top can be turned into an inner function of some vector space. Okay, so the way that you do it is, the way you make that transformation is you do a Taylor expansion of the exponential function. So start with the radial basis function kernel here, and let's just, to make things simpler, let's just set sigma to 1 over square root 2 so that they cancel out those constants. So all we have to think about is just the exponentiated negative squared distance between the two vectors. Okay, and using FOIL again, we can actually expand this out a little bit and isolate some easy to compute terms with some more complex terms. So we now have the vectors multiplied by themselves, all added together, and then the middle term, which is just 2 times the dot product of the two vectors with each other. So at this point, we can expand one of these exponential functions, the one on the right in particular, using the Taylor expansion formula, which for now we'll just treat as if it's true, which it is true, but I'm not going to prove it here. But we can just read off the formula and try to plug it in. So we end up with this. We end up with the terms that have to do with each vector multiplied by itself, all multiplied by this series here. And in the numerator of each series, you can see there's an xi transpose xj. There's a dot product of xi and xj, all taken to the nth power, which actually is very strongly related to the order n polynomial kernel. Now it's missing that +1, but this what that actually means is this is only going to have the order n terms and not any of the n-1, n-2, all the way to 1 terms. So it's just the order n terms of the order n polynomial kernel. So, and that's all multiplied by 2 to the n divided by n factorial, which are essentially just, you can think of them as just constant coefficients here. So let's think of this as phi n of x. So we'll use this notation to indicate the polynomial feature map of order n. And with that notation, which is a little clunky, we can actually write down what the RBF feature map shows you, which is going to be the product of the exponential of the terms with the vectors multiplied by themselves, all times the vector of every single polynomial kernel or polynomial feature map from 1 to infinity. So from left to right, it goes the linear feature map, the quadratic feature map, the third order feature map, all the way to the infinity order feature map, which doesn't really exist, but is there conceptually. So it's definitely really weird, but what this means is that there does exist some infinite dimensional space for which the Gaussian RBF kernel, which is up at the top, is an inner product in. So with that, I'll just show you the formulas again. You've already seen them, but I'll put them all in one place. So the linear kernel, which is the most basic one, is just the vector dotted with its with another vector. So in other words, it takes place in the same feature space as the input. The polynomial kernel is going to be the dot product of the two vectors plus 1 to the mth power, which maps to or corresponds to mapping the features into a polynomial expansion of the original input features. And the RBF kernel is computed by taking the exponential of the negative distance between the two vectors, scaled by a variance term. And that corresponds to this infinite polynomial expansion, which is pretty hard to wrap your head around, but does constitute a valid space for computing dot products. So then lastly, I'll just fill in some other important things that will come up when implementing these kernels, which is that if we have a data matrix instead of vectors one at a time, or two data matrices rather, we can compute the gram matrix, or the matrix of all the possible kernel values of the ij pairs, by using matrix computations. So the linear kernel gram matrix can be computed by taking the inner product of the two matrices. The polynomial kernel can be computed by taking the inner product of both of the two matrices, adding 1, and taking each element of that matrix to the mth power. And then lastly, the Gaussian RBF kernel can be computed by first computing the distance matrix between all the ij entries in the matrices, which is you can do it with this nifty trick in matrix form in the nested parentheses, and then just dividing that by 2 sigma and negating it and exponentiating that matrix. So these are all pretty lightweight computations considering the high dimensional representation we're going to be implicitly using with these types of kernel SVMs. So to wrap up, the idea behind the kernel method is to map the input data that you get into a new feature space that is usually going to be higher dimensional, because we're going to want to use the kernel trick to reason about more nuanced models of the data than the standard linear models. And we'll need to have an efficient method for computing the inner product in the mapped space, especially if it goes to a much higher dimensional space like in the RBF kernel. And then the idea is that whenever you have a method that uses the inner products, whether it's in a mapped space or in the original space, instead you directly use the kernel function. So you never actually have to compute these inner products. So the example of this and the whole motivation for this is the dual SVM, but there's actually a lot of other methods out there that can use the kernel trick. Okay, so next time we're going to talk about how to alleviate the computational cost of SVM training. In particular, we're going to look at how the quadratic program that we use to solve either the primal or the dual SVM is roughly a cubic time algorithm. It's not exactly that, and a lot of times it behaves better than this worst case bound, but in general it's quite expensive as a cubic time algorithm. So we'll find ways to get around that in the primal and the dual form.